last time?
You ended by giving some examples of some continued fractions that had like big digits, right? And that.
Right. So just to back that up even a little bit more, we looked at the inverse map, randomness of the inverse map. Inverse map A goes to A bar mod P, and we saw that this was random, and that came through studying Klusterman sums, which look like SP of NM is equal to a sum over A. Of course, that A has to be invertible to even think about this map, but then e to the 2 pi I over P, AN plus A bar M, which is like the two pieces. Okay. And then we saw this, we gave Klusterman's bound. We saw this was bounded by P to the 3/4 or something. So it should be of size 1. Of course, this is only if Mn is not equal to 0, 0.
And ultimately what you did was like a fourth moment.
Exactly.
Kind of knows what just hit the spot.
Exactly. Because it's a second moment of a square, and a square spectrally is a convolution.
Right, and we use that to our advantage.
And we use that to our advantage. And then we looked at, not the inverse map of multiplication, modular multiplication. What about multiplication? And here things were slightly more subtle. The map A goes to A times B mod P.
Right.
Was more subtle, and we saw that the quality of the randomness, we only saw this qualitatively and not yet quantitatively, the quality of randomness depended on the continued fraction expansion B over P as 1 over A1 plus 1 over A2 and so on, which we write as 0, A1, A2 up to A, whatever the length is.
And it graphs and mathematics, that was great.
Right. And in fact, so there's a theorem about this. So the theorem, this is due to Zaremba in the late 60s, I want to say 69-ish or something. Don't quote me on this. No, okay, quote me on this, whatever. Zaremba showed that the discrepancy, we talked about discrepancy, take a rectangle, yeah, the worst rectangle. The discrepancy, if you, as you run over the pairs, A over P, B times A over P, mod 1, these pairs, mod 1, as A ranges in Z mod P. So that's a set of P points. That the discrepancy of this is bounded by, let me be crude, this isn't exactly his theorem, but his theorem is roughly of the form, it's bounded by A times P log P. A is the max of the AJ. So whatever the largest partial quotient is, it's bounded by roughly that constant P log P over log P. It goes to 0. It goes to 0 very quickly, as long as A isn't large relative to P.
You mean like in practice?
Well, A could be, you could have a denominator P. We had a denominator that was of size 5,000 or something with an A that was of size 50, whatever it was. So it cut the quality of the discrepancy down by a lot.
So what you're saying is like, oh, right, okay, so the A implicitly can depend on the P.
A depends on, yeah, A is a function of B and P.
Right, yeah, okay.
It's a function of this quotient.
Yeah, exactly,
So it's not, now contrast this to, recall that Wolfgang Schmidt showed that this is at least some constant times log P over P, just for any sequence of P points. You won't get a discrepancy better, not only than 1 over P, which is trivial, but you won't get better than log P over P.
wait, why did we
I mentioned this and we didn't prove this. It takes some
Okay.
time to do.
Okay, so
But-
in general, it won't have to depend on this A.
Well, a lower bound, you can't do better.
Oh, wait, this is a lower bound.
A lower bound on the discrepancy is log P over P. And Zaremba says this particular sequence has discrepancy bounded by log P over P, which would be best possible if that A was a constant.
Exactly. Because if that weren't a constant, then maybe something crazy could happen. Right?
But A is A of B over P. Maybe that's a better way of writing it instead of trying to squeeze it in here. Is not a constant. Or is it? So here's Zaremba's conjecture, which he formulated a few years later after some numerical evidence. The conjecture is there exists some A so that for all, and by the way, I phrase this in terms of primes, but this actually has nothing to do with primes. This is P is an arbitrary integer.
Right. Yeah.
So in fact, let me change notation to
Continued fraction certainly still works.
everything still works. Yeah, multiplication, modular multiplication still works. So the conjecture is there is some constant value, A, so that for every denominator D, there exists B co-prime to it, such that the continued fraction of B over P, B over D, is 0 A1 through AL, and all the partial quotients AJ are bounded by A. So let's test our understanding of this. Right, of course, this is motivated by this conjecture. We want to make A an actual constant. And what you want to know is that there's some multiplier modulo every number, every prime, doesn't matter, every number, that makes this, that gives us a really strong discrepancy, really small discrepancy. It's a very equally distributed sequence. Okay, so let's look at this. So for example, well,
It makes these numbers hard to approximate, right?
these are the worst, yeah, the most badly approximable numbers. Yeah. The discrepancy, the conjecture, in fact, the conjectured value is 5. And that's because A is not equal to 4. This is for a trivial reason. So if you look at D equals 6, then your two numerators are 1 and 5. The only numbers co-prime to 6. Then B is either 1 or 5. And then the fractions are 1/6. B over D is 1/6, which has partial quotient 6, or 5/6. 5/6 is when you take the reciprocal of this, you get 1 over 6/5. And 6/5 is 1 plus 1/5. And so here, there's a quotient that's bigger than 4, and here there's a quotient that's bigger than 4, too big.
Okay, so sort of like the theoretical conjecture is like the very next thing, right?
So for this value of A, no one has ever exhibited, right? All it takes is to do exactly what we did, exhibit a value of D for which every possible value of B, which is a finite calculation, the partial quotients are always bigger than 5.
And experimentally, I guess.
People have done this out to quite some height, and they've never seen it. Now, so let's introduce a little bit of notation. Let R sub A be the set of these rational numbers, be the set of fractions B over D in lowest terms with partial quotients A1 through AL, all bounded by this parameter A. Okay, and then let D of A be these denominators, be the set of D integers D, so that there exists a B co-prime to D with B over D in RA. So we just showed what this means is that 6 is not in D4. So D4 is a set of all numbers where there exists some numerator to make all the partial quotients bounded by 4.
Right.
And for 6, it doesn't exist. So 6 is not in D4. Okay. And the conjecture question?
I don't know, I was just saying, think what the conjecture would be.
Right. So the conjecture will be D5 is everything, is all the naturals. Okay. Now, if you actually look at this, it'll take me a little too long to code this up. But if you actually look at pictures of this, and I'll point you guys to a paper where I have pictures of this. But a good thing to do is to look at, we're going to look at RA graded by D. In other words, a plot of D in this direction, going out to some, I don't know, capital N. And then the values, here's 1, this is 0, 1. And then every time I have a fraction B over D, I put that fraction at height, at X coordinate D. Okay.
Oh, you mean for that denominator?
For that denominator, yeah. So if we set A equal to 5, then we get some values. So in particular with D equals 6, I only get the number 5, 6. So when D equals over here is 6, over here is the fraction 5/6. So this is the point 6, 5, 6. So I'm putting D, B over D for every B over D in RA.
Okay.
And then, does that make sense?
So for every A, you get a different graph. Right?
For every A, you get a different graph. Yeah, I get a different graph depending on what A is.
Okay, and when A is grow, the graph change. How?
The graph, so if all the partial quotients are bounded by A, then those numbers are all contained in the partial quotients bounded by A plus 1, for example. So the graphs get thicker
Yes.
as A gets larger. Okay, and what you'll notice is that they sort of grow in certain directions. There are certain, there become certain bands, horizontal bands. And what those horizontal bands are, it's very interesting, are the limit set. So let L of RA, which I'll often denote instead as CA, be the set of limit points of RA. So what are the limit points of these fractions, of these rational numbers? How do you get a limit point of this? Well, it'll be some infinite sequence with all the partial quotients bounded by A. Those are exactly the things that are limits of finite sequences, all bounded by A, right? So this CA is the set of all not fractions, but just arbitrary numbers, A1, A2, infinite sequences with all partial quotients bounded by A. Okay, so now let's look at this then. So for example, let's look at A equals 2. You want to say something? Oh, Nick, you want to say something?
I'm a little confused. What's this graph that we've drawn?
So these are the pairs. This graph is the pairs D, B over D, as B over D arranges in RA. So I look at all the
And
fractions,
so we graph all such points in RA.
all such points.
Okay.
So above every D, let's look at the conjecture in another way. Above every D, you would like to know that there's at least one point.
Yep.
But this graphs all of the values of B so that B over D has partial quotients bounded by 5 or whatever. And so the conjecture is for A sufficiently large, the fiber above every D is positive, is not empty. Whereas when A is equal to 4, above 6, there's no points. Does that make sense?
Yes. Okay. I understand. Thank you.
So here's a fun way to see this Cantor set. So what does it mean that all the partial quotients are bounded by are 1s or 2s? Well, the first partial quotient Well, let's look at them one at a time. What does it mean that A1 is either 1 or 2? Where are the numbers that have A1 equal to 1? What does it mean for A1 to equal 1? It means you take the number, you take 1 over, the numbers between 0 and 1, you take 1 over that number, and you only shift once to get back into the unit interval, 0, 1. Well, that means you were at 1 to 2.
You were at?
When you took 1 over the number, so what's the continued fraction algorithm? You start with x, you take x, you replace it by 1 over x, and then you take the fractional part,
Yeah.
which means you subtract off the integer part.
Right.
And the amount that you subtract off is the partial quotient. These are the AJs as you iterate the map. So you start with the number x, you invert it, you wind up in some interval, you shift by 1, because that A1 is equal to 1. We're trying to understand where is it equal to 1, and then we get back here. So what does it mean that we shifted by 1? It means we were between 1 and 2. To shift by 1 and wind up inside 0, 1.
Yeah, so 1 over it is between 1 over 2, comma 1.
A half and 1, exactly. So between a half and 1, all of these numbers have A1 equal to 1. Because when you invert them, they wind up between 1 and 2. You shift once. How about we're also allowed for A1 to equal 2. So this is going to be in 1 or 2. When is A1 equal to 2?
Is 1,
Yes.
is it 1/3 to 1 over 2?
Yes, because you shift twice from 2 to 3 to get back here. So if you were in between 2 to 3, if your inverse, if your reciprocal is between 2 and 3, then you're between a third and a half. Okay, so between a third and a half, these are the numbers with a 1 equal to 2. Any number here has an A1 that's already too large.
Yeah.
Its inverse will be greater than 3. And so its first partial quotient will be greater than 3. So these numbers are all removed. Well, these are the very badly approximable. So they're the better approximable
Yeah.
than these. Yeah,
Yeah.
they're bad at being
Numbers
badly
makes sense.
approximable. Yeah.
Yeah, because it's more complicated, right? Because we have to look at A2.
Yep. Now we have to look at A2.
Yeah.
So again, A2 can be either 0 or 1. 1 or 2 rather.
Yeah.
So once you're in this interval, you've done A1, there's going to be some interval where A2 is equal to 1 and some other interval where A2 is equal to 2. And because of the reciprocal, it's going to go back, left instead of right. And then you cut out all of these. And similarly, if the A1 was equal to 2, there's some interval where A2 is equal to 1 and then where A2 is equal to 2, and then you cut out all of these.
Is this Cantor set going to be one of the measure 0 ones, or?
It will be measure 0
Okay.
because you're going to cut out all these intervals. And then you cut out more, and then you cut out more, and so on. And then you continue cutting things, and you get all these little circles that are diameters of intervals that are getting cut out. And so I like to think of this as starting in the upper half plane and falling down, and you sort of bounce around on these circles until eventually you land on the real line. And if you manage to get to the real line, then you're in the Cantor set.
What's the rule for bouncing?
There's no rule. It's just the set of all points that can be reached that come down and can be reached. Okay, so this is just one way to visualize. How do you visualize the Cantor set? Well, you can take all the intervals that have been removed and put circles on them, so you can see that that's where it's been removed. Okay, and in fact, that is exactly why you have these bands. The bands are the limit points. They're exactly they're approaching the set of limit points for large n. If you cut off the denominator at large n,
Like B over D is going to.
these are the sets of B's over D's that are converging to something in CA, into this limit set. Let me show you a picture.
Are these?
We changed the, I'm a little bit confused.
Yeah, we changed D.
And our continued fractions are getting arbitrarily long, then I guess this means that they'll converge to rational numbers.
Oh, come on. No, these are rational numbers that are converging to irrational numbers.
Yeah, that's what I mean, yeah.
These-
The continued fractions are gonna get longer and longer as you go, right, with ones or twos. Like, it's not gonna stop at a finite continued fraction, right?
It's
So
not
you're
going to stop at
get-
a finite continued fraction.
so
That's
you're
right.
gonna
It's
get
going to
an
keep going.
irrational number.
You're going to get an irrational and most of them will be transcendental. I mean, the periodic ones will be quadratic surds.
Right.
Sorry, why can't I find this picture? This will have a picture in it. Put a link to this, but just to show you a picture. This is what we've been discussing about discrepancy. Here's that Cantor set.
Is it a research or an expository?
This is an expository paper. So here is the case A equals 2 or A equals 5. So A equals 2. I guess I've done it vertically instead of horizontally, but you see these bands. And this is exactly going in the direction of the Cantor set.
Oh, okay, so what you're saying is the blank parts are the parts where.
Those are the intervals that are forbidden.
with the circle.
Yep.
Oh, I see,
So this will have. So if we were to paint the dots smaller and smaller, it would seem as it has measure 0.
Yes, as you go farther and farther out.
Because
You
you
go-
get more and more things blocking in the middle.
Yep. More and more intervals are being cut out. Okay. So here's a basic question. How many points are in one of these pictures? So let's say, let's R A of n. Sorry? Oh.
Yeah.
Barcodes, I like it. Let RA of n be the set of these fractions B over A in RA in lowest terms with D bounded by n. Just to make this a finite set. RA is an infinite set, but let's truncate it just like we do when we make a picture. So here's a basic question. What is the size of RA of n? How many points are there in this picture as a function of n?
Mm.
So a trivial bound, can someone give me a trivial bound for the size of RA of n? Well, what if there was no restriction on the numerator versus the denominator? So the numerator ranges from 1 to d,
N squared.
n squared, yeah. So trivially it's bounded by n squared. But it turns out it has a growth rate. And do I want to do,
It'd be sad if we can do better than this.
what's that?
It'd be sad or maybe amazing if we can do better.
We can definitely do much better.
Coprime B, right?
This is, yes, here I'm always thinking of B as being coprime to D.
Yeah, so we can definitely do better, at least from that.
But like for when you do coprime numbers, doesn't it grow like with a square as well?
It still grows, yeah, with a leading order too.
Yeah,
I just want to know the sort of
yeah,
leading order of this.
like some sort of weird-
Yeah.
So-
So how could you try to estimate something like this? So to study this, let's consider the L function, L A of S, which is the L function where you sum over D's, D to the S. And then what we want to do is capture what the numerator is, what the multiplicity of each D is. In other words, exactly what the size of this fiber is. Okay, so let's call that M sub A of D. So M sub A of D is the multiplicity.
This is kind of insane.
Well, you'll see in a second. So this is the number of B's. No,
Okay, so you can't like get an Euler product.
there's no Euler product. Yeah, it's not really an L function. It's more like a Poincare series.
Okay.
So this is the multiplicity. This is the set of B's co-prime to D, so that B over D is in RA. So it's the count above D. Why do I want to count that? Why do I want to consider the cell function? Then, well, in particular, if we sum D's up to N of these multiplicities, what do we get?
You get the RA.
You get exactly the number of RANs.
Some there.
Again, going to this picture, the number of D, the cardinality of this set is the multiplicity of D.
Oh.
And now
yeah,
I
yeah.
sum over the D's up to N. Of course, that's how many points there were in the picture.
Partitioning them.
I'm just partitioning, I'm grading them by the denominator. Okay, so that's the thing that I've turned into an L function so that I can try to apply Tauberian theorems.
I see.
If I know something about the polar behavior, if I have an analytic continuation and a polar behavior of this, then I can try to say something.
Seems kind of strange, you know, it's like you, can you in general, like, what would you need in order to, like, what do you need of the constants above for an L series in order to, get like an analytic continuation?
So
Is there any nice condition?
yeah, that's a good question. When they have Euler products, then there is a condition that restricts them. These will not have Euler products, but they will have something else. So I want to tell you Landau's lemma.
It just seems like, it's hard to me to think like, oh, you take a problem, right? You turn it into a series, and when would you think, okay, maybe I can do something more than algebraic manipulation, right?
Right.
Combinatorics. You can then do analysis.
Here you can do some geometry and analysis and dynamics.
It's crazy.
So so let me tell you Landau's lemma. Landau's lemma, which is very useful in all kinds of things, but it relates to L functions, arbitrary L functions, just Dirichlet series with non-negative coefficients. So the key thing about all of these guys is that they're non-negative. The multiplicity could be 0, but they're not negative. The Landau lemma says the following: given a Dirichlet series, let's call it just f of s. So it's some sum of a n to the s with non-negative coefficients. The a n's are all non-negative. And suppose it converges in some half plane. Converges absolutely in some real part of S bigger than some constant. Okay, so I'm thinking of some constant over here, and I know that it converges absolutely in some region. I mean, okay, if the coefficients are e to the n, it doesn't converge anywhere. Fine, I don't want that. Then I have nothing to say.
This is already like really nice.
Just yeah.
It'd be nice
but-
assumption so far.
Yeah, like the absolute convergence is like strong, right? This will give us the, this will give us like,
It's not A, it's not negative, no, it's not strong, the absolute curve, it's not.
The absolute convergence is just yeah, because when you put absolute values, all you get is n to the sigma. The ANs are, as you said, non-negative, so they're not going to contribute to any convergence. And all this means is that the ANs roughly don't grow faster than the polynomial. If they grow slower than, well, if they grow like some polynomial, then that tells you where the cutoff is. If these are less than n to the 100, then at what, 101 and higher, this thing converges. Okay, so we're given a Dirichlet series. The coefficients are non-negative and it converges somewhere. If it has an extension, it has a holomorphic continuation to some neighborhood of C, if it extends holomorphically to any tiny neighborhood of C, then, so that's a big if, then it converges absolutely, then there exists an epsilon, such that F also, the series defining F also converges absolutely for real part of S greater than C minus epsilon. So if you can, if this function, the input is non-negative Fourier coefficients, and there's some absolute region of absolute convergence, if their function has holomorphic continuation by some other method to a slightly larger region around C, then there's some epsilon, so that actually you get an entire new region of the original function converging absolutely. You give me an inch, I'll take a mile. Now notice, this is absolutely false already for our favorite Dirichlet L functions, or Dirichlet L functions. Right? A Dirichlet L function will converge up to 1. It has holomorphic continuation, but it does not converge absolutely inside of 1. So what's wrong?
You mean like for Zeta we're talking about, or?
No, not Zeta, because Zeta has a pole at 1.
Right,
But these are all entire.
right.
These are entire, and they converge down to 1. They have an absolute convergence to the right of 1. They have holomorphic continuation, not only at 1, but everywhere, they're entire functions, but they do not converge absolutely inside of 1.
Mhm. But they do.
It's the positivity.
Yeah, I mean, there's nothing else.
There's nothing else, right?
They
Right.
do converge
So-
from 0 to 1, right?
Conditionally.
Conditionally,
Not absolutely.
right? And then like
So-
the conditional range cannot be too far from the absolute range also, so.
Yeah, but here we want absolute convergence. So I'm claiming not only, so the fact that this converges to real part greater than C, you were just wrong. It converges a little farther.
I had a question about like the earlier
Yeah.
statement though. So it's like if you assume this absolute convergence, right, that already gives you some analytic properties of f of s, right? Because you'll get like, say if your ANs are bounded by a polynomial or something, right? Then that will give you like convergence on like uniform convergence on compact sets. So you will get like this will be holomorphic on like a half plane.
Yes.
Really what you're investigating is what about everywhere else is what you're asking.
I'm saying that, okay, it's holomorphic in a half plane. It does not need to have holomorphic continuation beyond this point.
Right.
There's no reason. I mean, if I just make some arbitrary L function here, it could very well blow up at this point, like Zeta. Zeta blows up at that point. It does not have holomorphic continuation past it. It has meromorphic continuation, not holomorphic.
Yeah.
If there's some way to get it to be holomorphic inside of that point, actually, you'll get the whole strip.
Yeah.
But you still have to prove for the neighborhood, right?
I-
Always difference of, I guess, yeah.
yeah. So I'm assuming it's holomorphic in a neighborhood of C.
Okay, that could be difficult. Yeah.
So this is sort of telling you that, oh, you have series usually work in half planes, and so this is telling you that finding a small neighborhood shouldn't change if this will happen in a half plane.
That's right. The real boundary of where it converges is farther in than you gave me. You originally only gave me C, but actually there's more.
Yeah.
Okay. So let's see how to prove this. Is very simple.
Wait, hang on. Then one last thing to
Please.
clarify. So if you know you found a line where it converges absolutely, you know that to the left of your line it does not converge absolutely, then you know there's no holomorphic continuation in the neighborhood of your boundary.
That's right.
Okay.
That's right. If you have some way to prove that it can't converge absolutely, then there can't be holomorphic continuation if you have non-negative coefficients in a neighborhood of the real value of that point. Okay.
Yeah. Maybe it's just good to emphasize we're talking about the real value, right?
Yes, C is the
Like,
real.
yes.
Yes. See, we're just looking right at the real point. That's all we need.
Like zeta has a holomorphic continuation away from the real line.
That's right.
Across. It's
That's right. Zeta has continuation here, but that's not going to be good enough for us. Yep. Thanks, Louis. Thanks for clarifying. So
You
this
can't
is
do
not
something
good.
like shift zeta up by I because that now it's no longer given by a Dirichlet series.
It is still given by Dirichlet series, but the coefficients are n to the IT. If you want to shift it up by I.
They're not real.
They're not real and they're not non-negative. Yeah, so we will absolutely have to make crucial use of the non-negativity. Exactly. Okay, so let's see the proof. All right, so let me leave it as an exercise. Exercise that you can assume that C equals 0 just by shifting. Okay, it's a trivial exercise. So now we're saying we converge all the way to the real part of S greater than 0. What's that?
Yeah, you're just shifting by your real
I'm just shifting by. So we converge all the way down to 0, and we have a little neighborhood around 0. These are the two things that we need. I'm going to take the point 1, and I'm going to look at the power series, a Taylor series expansion. Taylor series expansion of F around 1. Okay, so what is that? Well, it's just trivial. A sum over K, the kth derivative at 1 over K factorial times S minus 1, it's the series about 1 to the K. All right. Remember what we learned in complex analysis. A Taylor series expansion converges absolutely on the largest radius that contains, so this converges.
At least radius 1. Well, I guess, yeah, at least radius 1, I guess.
It does converge for radius 1. It actually converges because of the nature of circles. It converges on some slightly larger radius because the function is holomorphic. What is that?
And then you go to 2.
And well, in other words, so let's say that this point is minus epsilon. So maybe this is minus 10 epsilon or something. Okay, so this point is minus epsilon, converges absolutely for S minus 1 less than 1 plus epsilon for some epsilon. Okay, now let's work out what that derivative is. What is the derivative of F? Remember, F is a series. F is a series an times e to the minus s, with e to the minus s log n.
We've already assumed that we have a holomorphic continuation around 0.
Yeah, so that's the assumption. Assume.
Okay. Yeah. Okay.
has-
Okay. We've already assumed that. Okay.
We've already assumed that. Yeah. So I'm taking these two assumptions. Now I need to give you an epsilon.
Okay. And
So
that's why
I
we
think
can
this is an epsilon. So this epsilon is the epsilon.
Right, we didn't have a continuation then.
If we don't have a
I think we
continuation,
say the series will converge further than.
if we don't have a continuation, then I can't say anything about it. So this is just the original function. I want to differentiate k times. Nice thing about this is I know how to differentiate e to the minus s log n k times with respect to s. It's just minus log n will come down k times. That's all there is to it. Okay, and then I can evaluate this at s equals 1. At s equals 1, what do I get? A sum over n, an times minus log n to the k. This is really minus 1 to the k log n to the k. And then e to the minus log n, which is just over n. That's what the derivative is. Now this converges absolutely. So I want to evaluate this at minus epsilon. F of minus epsilon converges absolutely. But what is it? It's a sum over k, 1 over k factorial. S is minus epsilon, so this is minus epsilon minus 1 to the kth power. So that's 1 plus epsilon to the kth power times minus 1 to the kth power. And then I have to put in f the derivative, the kth derivative of f, which I have right here. It's a sum over n, an log n to the k over n, and a minus 1 to the k.
Oh, from.
The minus 1 to the k cancels this minus 1 to the k. Now this converges absolutely. Switch orders, and I have a sum over n, an over n, and then a sum over k. I have a 1 over k factorial, 1 plus epsilon to the k, and a log n to the k. So let me make that a 1 plus epsilon times log n to the k. So far, so good. But what is this?
Wait,
E,
The 1 plus epsilon over. Guess n to the 1 plus epsilon.
this is exactly n to the 1 plus epsilon. Beautiful. Well, what does that mean? That means that the sum over n, an over n times n to the 1 plus epsilon converges absolutely.
Everything is positive.
Everything's positive. But this is the sum over n, an, the n on top and bottom cancel, and I have n to the minus epsilon. Which is exactly the convergence at this point. That gives me absolute convergence everywhere.
oh, like looking at the series?
Yeah, because that's what the series at minus epsilon would be. It would be an over n to the epsilon plus it. But in absolute value, that's just an over n to the minus epsilon.
Right. 'cause
T
it's
doesn't,
under the
T
zero.
has absolute value 1. N to the it has absolute value 1. So F converges absolutely on real part of S greater than minus epsilon.
That's something that seems like a little strange about, like, is this what's proven to use, I mean, is this what's used to prove that, like, there is like a furthest half plane or it converges everywhere? Or am I thinking about this circularly?
No, that's exactly what this is used for. If you have a Dirichlet series, so corollary,
Because I was thinking about this corollary the entire time, and I was like, why are we doing this? But that's because we use this to prove that.
right? If F is a Dirichlet series with non-negative coefficients, then it has an abscissa of convergence. Then it has an abscissa of convergence, i.e., there exists some sigma such that F converges absolutely on real part of S greater than sigma and not on real part of S less than sigma. So it has there's some place beyond which the series can't converge.
Is there
Okay.
like some sort of example of, I don't know, some nasty series which will converge, say, I mean, with nasty coefficients, I guess, that will converge, say, on some half plane and then some strip somewhere else, but nowhere else?
Oh, with weird coefficients,
I mean, that's what you
with
would
non-negative
mean, right?
coefficients, yeah.
I mean, even something like this, right? Always like that, and no one else.
Right, right. You can imagine, exactly. You can imagine that it converges, might imagine that it converges on some weird shape, exactly as you said.
Yeah.
Some weird shape like this, and then a half plane.
Yeah,
Right.
Okay, so that can't happen
that can happen
if you have non-negative coefficients.
But if you don't, maybe it can.
Yeah, then anything
Yeah, so I guess if you don't have non-negative coefficients, if in practice, you can still use, other properties, then it won't matter, I guess.
In fact, the shifted zeta function has exactly this property. The shifted zeta function has can converge on it has this region on the one line. Well, it's not quite the same thing. Oh, I just mean zeta. I just mean zeta of what 1 plus IT plus S.
Oh, yeah, okay.
Right. This is what Lewis's comment was. That this is a function that has that's over here at 1 plus IT. It converges over here. It has holomorphic continuation, but there's nothing, you can't get convergence inside. Precisely because its coefficients are n to the IT or n to the minus IT, which are not non-negative.
You're gonna hit like pole.
Exactly. There's a pole down here that you can't escape.
So where do we use the fact that they again are positive exactly in the group?
Yes.
In the first place, right?
Just for this.
It's right here. So this absolute convergence, in principle, to see the absolute convergence, we would need to take absolute values.
Here everything's.
Here, everything's already positive.
And.
So it's this absolute value that I don't need to place. It's in reversing orders and not putting absolute values on the AN.
Yeah, so
Okay.
probably one of these switches might not work if your coefficients worked out to be something strange.
Right.
That's like,
Right. It'd be, I don't know of an example that has what you're suggesting, some kind of, region here and a region here where it has absolute convergence, but not in between.
I guess it's like sort of you develop the theory, I guess the number theory, so that in practice you be able to do whatever analysis you want to do, right? So it's like,
Sure.
if you don't have examples that require functions like these, then I guess it isn't like, really, if there isn't a phenomenon that is modeled by some sort of function like this, then why would we go out of our way to study it? Like,
Yeah.
But you're right.
So what does that say about this series?
Okay, so
Yeah.
I mean, I think one thing is that like usually what happens, right, is like you have a region of conditional convergence after that.
There could be a region of conditional convergence. That's right.
Like for non-negative function. I mean for not non-negative functions.
Right. Like Dirichlet functions, for example.
Yeah, but I would guess that something like what Andre is saying is probably not going to happen.
Yeah,
so I
whenever you
don't know
have
for
a
sure off
region-
the top of my head, but like it's sort of like saying that the coefficients have to like correlate with the phases in that strip exactly.
Yes.
But like they're probably just going to be, even if they do that, they're going to be like dominated by phases with like larger real part. So
Yeah,
it would have been converging anyway.
So one thing that's even easier to see actually, if it converges if it converges absolutely at real part of S equals something,
Yeah, then it has to like.
then it has to converge anywhere to the right.
Yeah, so you need so that's why I meant like you'd have some sort of crazy conditional.
Yeah, if it has condition, yeah, conditional convergence can do all kinds of.
Right, the absolute thing, that's why we have half planes, right? Because absolute convergence like is so strong, right?
Yep.
It gives us all that, but I don't know. Yeah, anyhow, this is
Nick,
at this point, you might not even have like analytic properties to like do things with possibly.
Nick,
Clarify one last thing. Where we're using that the coefficients are positive is because in that last step where we have an over n to the minus epsilon, each term is the absolute value of an over n to the minus epsilon plus it. And that's why it's like the absolute, summing absolute value for s,
Yeah,
whatever
so-
we want.
so the
Sure.
absolute convergence here, what does that mean? It means that if we take absolute values inside, so we have this 1 over k factorial this thing, if I took absolute values here, that would converge.
Yep.
but actually everything here is non-negative.
You just push it in.
So I can just drop the absolute values.
Yep.
And I'm not getting any cancellation in the sum that's making it converge. These things are already, everything is non-negative, so I can drop the absolute values and reverse orders.
Hmm. Okay, but then we use that the ands are positive again, right at the very, very end.
Yes.
Yeah, right there, to say that that sum is the sum in absolute value.
Right.
Yeah,
So that
but
when
we
we're
also put like
checking
absolute value n to the minus epsilon plus it
Yes. Yes.
in the denominator. It could be like
yeah.
n to the minus epsilon plus it.
Let me
And
make
now
some
we've shown that it
room.
converges absolutely for anything in that strip. Yeah, that. Okay. And we're also using that ANs are positive there, right?
Yes, exactly.
Okay.
For this to be an equal sign and not a less than sign, because I have the,
Yeah.
I know
Okay.
that it's bounded from this side. I want to know that this thing is bounded, but these two things are equal.
Right.
Okay, so back to this weird non-L function, a sum of d to the s with its multiplicities. What can we say?
So you had a trivial bound, right?
I had a trivial bound. I had a trivial bound for the number of elements of Ra of n, which is also the sum of the MADs, d up to n. The trivial bound was n squared.
Right.
So this L function converges absolutely for s bigger than, real part of s bigger than 2. Exactly. Exactly. And it has some abscissa of convergence. This has some abscissa of convergence at, let's say, sigma. Of course, sigma depends on A. And it turns out, so these Cantor sets CA have some Hausdorff dimension. Let's call it delta A, is the Hausdorff dimension of the CAs. So for example, this C2, this Hausdorff dimension has been studied since the 40s. And people worked out what it is. It's something like 0.531 something. Okay, it's just some number, like, you know, it's not something that you can write down in terms of logs. It's as good as any, yeah. It's some number. And it turns out, and it's not too hard to see this. Let me not go into it. We'd have to like talk about Hausdorff measures and dimensions, but it turns out that this is twice the Hausdorff dimension. So if you think about A getting large, by the way, I should have said that back up here. Well, let me.
Somewhere where like Hausdorff dimension is coming in practice to like mean something.
Yes.
Like geometric.
Yes.
Right?
Exactly. Exactly. So if we take one little aside, if we take the union over all A's of these Cantor sets, what is this?
Fill in everything.
You might think so, but every one of these Cantor sets has numbers that are uniformly badly
Oh,
approximable.
also, like if these have actual of A measure 0, the union is gonna have to measure 0.
Because it's this countable union.
Yeah, so it certainly cannot be everything.
Cannot be everything. So what is it? This is exactly the set of badly approximable numbers. Numbers whose partial quotients are bounded. I don't say bounded by what.
It's true. Yeah.
Whatever it is that they're bounded by, it'll be caught in one of these Cantor sets.
This won't catch the majority of numbers which
That's right.
have like some crazy expansion.
That's right. So this is your typical, this is like the first example people meet of something with measure 0. So this, let's call this C. The Lebesgue measure of C is 0, but the Hausdorff dimension of C is 1. So it has full Hausdorff dimension while being, as a Lebesgue set, being empty.
intuitively, since you're not going to get into all the Hausdorff dimensions, so intuitively, what should it mean if your Hausdorff dimension were a half, say? Like, what should that tell you?
Well,
Or maybe before answering that, can you loosely
Yes.
describe what the Hausdorff dimension is?
yes.
Always seen it thrown around. I've never actually seen a definition.
Okay, so we need to talk about Hausdorff measures. In fact, I gave, I'll point you to the end of my real analysis lectures. I go into Hausdorff measure and Hausdorff dimension. I'll point you to a link to that.
Okay.
But roughly speaking, it's like, that's why it's almost the same as this abscisive convergence. It's the smallest value for which when you cover, so you take your set, you cover it by balls of certain radii, and you want to know that the what the power of the radii is, what's the smallest power, so that the sum of the radii to that power converges.
Oh boy, yes, it's almost like.
It's very, very similar to this
almost by
abscissa.
definition.
Yeah, it's almost definitionally the abscissa, and then there's some factor that goes between.
So this really makes you ask the question: was this Hausdorff's dimension stuff created to study things like this? If it's so similar and it like pops up right like that,
Hausdorff is more like 19 teens and 20s and 30s, right? He was killed by Nazis, so that's already, or he committed suicide when he was about to be.
right, so it was already late 30s, early 40s.
That by then, but he was already not such a spring chicken. I think the Hausdorff measure development is like 19 teens. This stuff, people, the badly approximable. I mean, okay, the High-Fancy approximation since Dirichlet, people have been thinking about, if not ancient Greeks and so on, Chinese and Indians. But this particular working out this Hausdorff dimension, like I said, people in the 40s were already thinking about these like uniformly badly approximable numbers and
Right,
studying
so
these
this idea
Cantor
was
sets.
already in their heads when they're coming up with these measures.
But Hausdorff is before that,
Okay, so you're saying
so
that.
it's a little.
I'm just wondering, what was Hausdorff dimension, right? What was Hausdorff trying to, what were people in that time? trying
Yeah,
to solve with
well,
this?
Julia was studying Julia sets, and people were looking at limit sets of
These
Kleinian groups
fractals
and
and-
fractal. Yeah, fractals were, people think Mandelbrot invented fractals in the 80s. He programmed it on a computer and let the world see their beauty, but Julia had these pictures in his head.
So it's sort of like they wanted some sort of way to compare these
Yeah,
without saying they're measure zero and Lebesgue, right? So it's like that.
right. You want a finer measure.
To like say something about these. Okay.
Right.
So you're saying that it's sort of fractals that sort of initiated the study for these.
Yeah, like Julia's work.
And it so happens they coincide with this like L function thing.
Well, I'm calling it an L function because to make it look familiar to us, and the techniques. So these Tauberian theorems that we're about to discuss are very familiar to us.
I just find it incredible that somebody found like this intuitive connection, I guess, between these. I guess you do have a fractal here. I guess it's sort of
Yeah.
okay.
Yeah.
Anyway, sorry.
So these Hausdorff dimensions, delta A, they approach 1 as A gets large, as A goes to infinity. Of course, these are nested sets. So,
Right.
all right. And so the point is, when A gets all the way to Hausdorff dimension 1, that's when we're approaching this n squared. So I'm just justifying this factor of 2.
Oh, okay.
That the abscissa convergence is twice the Hausdorff dimension.
That comes from the n squared trivial bound, is what you're saying? Or-
It comes from working out what Hausdorff dimension is versus what abscissa is, and that here that we have a factor of d to the s.
And in this case that you said for C2 or whatever, how hard is it in practice to, like, how hard was it of an exercise is it to actually compute?
Well, given that in the 40s they had 3 decimal places, it's not too hard. Now we have 100 decimal places with a click of a button. So there are new techniques for estimating the Hausdorff dimensions of these things. But that's a whole other subject.
The setting it up is not horrible.
It's not horrible. It's not horrible. Okay, so what was the point of all of this? So what is the number RA of n? How do you get it from the L function? How do you get the sum over the coefficients out of an L function? This is our bread and butter. You take your L function.
Alex Karlovich's thesis.
For what? His was about finding the automorphic forms and using them to compute. Yeah, here there aren't going to be automorphic forms. Actually, it's going to be something slightly trickier. Okay, so you take your L function, you multiply it by x to the s, or I guess I'm using n as a parameter now. So n to the s ds, integrate over some vertical line like 2, where it does converge absolutely, and divide by 1 over 2 pi I. Again, I'm ignoring convergence issues. This is
Mellon inverse.
it's just the Mellon inverse transform of the L function. Because that's exactly this n to the s over d to the s will exactly turn into d is less than n. And then the coefficients just pull out.
Intuitively, like we saw with the prime number theorem and the Perron kind of thing.
Right,
Then you could identify it like this.
exactly. So if you can pull the contours without passing any poles, then so pull contour to real part of S is equal to 2 delta plus epsilon. That tells you that the number of points is bounded above, not just by n squared, but n to the 2 delta plus epsilon. Moreover, if you could pull the contour inside,
Wait, why would you get that down?
just by putting absolute values in here. If the real part of S is n to the 2 delta plus epsilon. I'm ignoring all kinds of convergence issues, but just to first order.
But I don't think I'm seeing the first order.
So if we put absolute values in here,
Right.
the leading order of n
It's gonna be.
is going to be its absolute value, and the absolute value is its real part.
Right, but then what about the rest of it? Like the LA, S?
Yeah, you have to deal with the rest of it. So I'm not putting in the convergence factors that you need in order to deal with it, and then removing smoothing and unsmoothing.
Okay, so you're saying, like, for example, if this could be approximated by, say, some constant times.
Right.
You're saying n to the 2 delta.
Yeah, put it in a nice function phi that makes this converge, and then remove it.
Okay.
So I'm not. Let's not do that, because I just want a rough approximation to how many points there are. On the other hand, or conversely, if the number of points of RAN were less than n to the 2 delta minus epsilon, asymptotically, then the L function would converge absolutely. Then LA of S would
Yes.
converge absolutely beyond its abscissa.
Isn't the abscissa, you're not defining the abscissa as the leftmost you can go?
It is the leftmost that can go. In other words, this
has
can't
to be
hold.
it, right?
This, yeah, exactly. So what that means, if you put these two together, what that means is the number of points is let's write it crudely, n to the 2 delta A plus little o1. So the growth rate of this set is n to the twice Hausdorff dimension.
And then in this case, you were saying, well, but in this case, you said something like delta A was 1.
When A goes to infinity, delta A goes to 1.
Okay, and that would recover you the trivial bound.
That would recover the trivial bound, and that trivial bound would be true because that's how many badly approximable numbers there are.
Okay. But then if you're going less, then you might be able to get a smaller dimension.
Hausdorff
Okay.
dimension, exactly.
And that's where you get, and this would be the truth.
And that's the
right?
truth. It is what it is. The number of points that are being plotted in these pictures, the number of points that the computer plotted here is 1,000 raised to the twice the Hausdorff dimension of this 5 Cantor set. And here it's I went up to 10,000 because it's very thin. This A equals 2 Cantor set is much thinner. So that's how many points are being plotted. Now let's see what that means for the multiplicity. So what do we expect? What might, should, might we expect for each individual multiplicity?
Oh, here it's this is sort of like an average.
An average, exactly. So let's go back to this picture. D goes up to capital N, and then we have all these dots.
Before you continue,
Yes.
you said that as alpha grows, delta alpha goes to 1.
Yes,
So we go closer to the dumb bound, right?
yes.
The bigger the alpha.
And that dumb bound is the truth when A goes to
When
infinity.
you take all those unions all together.
Okay.
Because every rational number is badly approximable for some A.
Yeah.
So you get all the rationals. You can't do better than N squared.
The coprimality thing you were saying.
Yeah,
it won't buy you anything.
Yeah,
much better.
because phi of
Yeah.
prime you got to together. Right?
So you have some D's, and remember, this is counting the multiplicity. So there's a map. There's a map from the fractions. There's a map from RA to DA. Right? It takes fraction B over D in lowest terms here and just sends it to the point D in here. And so the question is, what's the size of the fiber of that map? What's the pre-image? That's this multiplicity. Now the total number of points upstairs, total number of points here, we just said, is n to the 2 delta.
That's all the points. you
All the
have
points.
here, right?
All of these points, the number of these is n to the 2 delta. Now for a typical D of size capital N, let's say between n and n over 2 or something, there's still n to the 2 delta points, roughly. And so are all of them going to land on very few D's? Or you have sort of two universes. Universe one is that all of the points, so what happens?
Yeah, can you like discard almost everything landing on like 1D?
Exactly. Universe one is that very few D's are hit very often. Right? I need these multiplicities to add up to n to the 2 delta,
Or they can be spread out.
or they could be spread out. Right? So universe two, every D is hit roughly the same number of times,
Or something between.
or something in between. Yeah. D's of size n are hit roughly, there's no conspiracy, roughly equal.
Yeah, the sort of the discrepancy sort of.
A different kind of a discrepancy
different
than
kind,
that,
I
yeah.
guess.
Well, which would you bet money on?
No conspiracy.
No conspiracy, right? So if we're in universe two, this would tell us that a typical multiplicity should be, let's say D is of size n, should be the total number of points, which is n to the 2 delta, divided by how many points there are in an interval.
Right.
Okay. And so in fact, now remember what delta 2 was 0.531. So this multiplicity, it's n to the 2 delta minus 1. That's the exponent.
That's just gonna be very close to 0,
But positive,
but not really, yes.
which means that already for a equals 2, twice delta 2 minus 1 is positive.
Yes.
Small, but positive.
In this case.
So for n large, the multiplicity should be some power of D. If D and N are roughly, I'm thinking of D and N as being the same order. In particular, for N and D of size N large, the multiplicity should go to infinity. I mean, should grow.
Oh.
And if it should grow, as N grows, then at some point it should become strictly bigger than 0. And if it's strictly bigger than 0, then that number D is actually represented.
Yeah, but how do we show where there's right?
We don't know. We don't know. Yeah, we don't know how to do
How do we know what?
that. We're in universe 2. The universe 2.
Right. That's, so you're saying that if we had a universe 2, we could settle the conjecture?
Yeah.
Basically, yes. Universe 2 is the conjecture.
There's so many things in between 1 and 2, though, you know?
There are many things in between 1 and 2.
You can have like some strip where it behaves like 2, and then like 1 or 2 Ds that have like a huge stack of
Yeah.
them, you know?
I
So
mean, yeah, you don't have to prove MADs it's like that. You can prove something weaker.
Something much weaker and still do it. Absolutely. Well, so let me tell you. So this led Hensley. So this, by the way, this result is due to Hensley, this observation in '89, and around the same time, for a completely different reason, Lally also worked out something that could have been used on this problem. It's basically it's the thermodynamic formalism. I gave a course on this a couple of years ago here. Maybe Lewis attended it. I can't remember how long ago it was. I know Edna did. Anyway, so let me not. I want to move to. This was supposed to be a little bit of story time. It's turned into a lot of story
Can
time.
you just say the title again of the course?
Thermodynamics, the thermodynamic formalism, Rel transfer operators, and their application to. So the way that you really do this is through Rel transfer operators,
Okay. Sounds good.
which, okay, we can talk about a little bit later. It's the substitute for automorphic forms and the spectral theory of automorphic forms when you don't have automorphic forms. Semester before you arrived, 5 years ago, that's too bad.
either that or it could have lined up with a first year class that was not.
Maybe. Anyway, so Hensley, given this, Hensley conjectured, I think in '92, that already, if you look at the denominators that have 1s and 2s, the denominators for which there's a fraction with all partial quotients just 1s and 2s, already that will contain, okay, it's going to miss some numbers, it's going to miss 6, it's going to miss some small numbers, but eventually it should contain every sufficiently large number. So the conjecture is that this already contains every sufficiently large number.
And experimentally, like when does this seem to happen?
I think I ran some experiments. There's still some values of D that are missing fibers high up,
Very high up, okay.
pretty high up. Yeah, it's going to take a long time because the multiplicity is so tiny.
Right.
And that's just the expected multiplicity in the glorious utopia of universe 2.
Wait, and then if you looked at delta 3, you would expect this dimension to be larger,
Yes,
right? And so then this would be
certainly if delta
easier.
2, yes, they get easier the larger D is. So for D equals 5, there's no gap. There's no known gap. Every single, here I've drawn it horizontally, every single horizontal ray has some B's in it.
And what is, wait, so would that mean delta 5 would be 1?
No.
Or-
Delta 5 is the dimension of this limit set. So this is still a Cantor set.
Well, what is delta 5? Is there any estimate for it?
Yeah, it's 0.79 or something. I don't remember off the top of my head.
That's interesting.
It's some number.
Some number, but it could be, for some reason, good enough to represent everything.
That's right. Well, the fact that it represents not just every sufficiently large number, but literally every number, that's an accident of this number 6. And there's two other numbers that are known not to be in D4.
And so you think that if a proof were to come along, saying, okay, this actually works for 5, you think it wouldn't depend on, you think this would actually be an accident and have no other like.
Well, it would be an accident for small
reason?
numbers.
Well, accident for smaller numbers, I guess, or I don't know. Things just work so strangely.
No, the truth should be D2. It should be that there's a finite list of numbers that are not in D2, and then after that, every number is.
Be incredible to see, and this could turn into one of these like Fermat prime kind of problems, right? Are they finite? And like, if so, which one's the last one?
Which one's the
right?
last one, right?
It could be
Right.
like, we could prove they're finite and never know like which one's the last one.
Right.
Ooh.
Or I imagine it going more like a ternary Goldbach, where, if Vinogradov proved 100 years ago that every sufficiently large odd number is the sum of 3 primes. And then over years, people whittled that down, whittled that down, whittled that down, and finally, okay, we're close enough that we can do a massive computer computation and just close the whole thing.
Wait, did it get close?
Yeah, Turner-Goldbach, yeah.
Which one's the largest?
Every number above whatever, I guess 3 is not a sum of 3 primes, but 5, 7. Okay, there's some small numbers that are depending on your definition of primes.
So you can just point at it and be like, okay, it's like from here on.
Yeah, yeah.
Oh boy.
9 is 3 plus 3 plus 3. Okay, so from 9 on,
And so
every
they just
number
they were able to use computers to like cut down the search to something possible, and then like,
yeah,
so what is it? You use theory in order to give like to deal with the infinity.
eventually, yep.
And then like you use computers to deal with the rest.
Yes.
Once your constants are, small enough.
Yeah, exactly. The first versions of these, the constants were ineffective.
Yeah, they exist.
So you couldn't, well, they don't even, you can't even write them down numerically. They depend on whether RH is true or false. Then people removed that and you got 10 to the 500.
Right.
And then you whittle your way down to 10 to the 20. And then you do some very clever things to compute, massively parallelize and so on.
That's incredible.
So anyway, so if it were to happen for this problem, this is how it would go. But let me just say, we're not even close to this. What we know so far, and this is due to Bergen and myself in 2014, I think it came out, is that there exists some A. There exists.
Is this like thesis related work, or was this after? Oh, it was after.
After. There exists some A. I think we got A equals 50, but since then people have whittled this down to A equals 5, such that 100% of the numbers, 100% of numbers are in dA. In other words, if you look at the number of elements in dA up to n, that is equal to n. That's asymptotic to n. In other words, if I divide this by n, this goes to 1. So I want to give you some hints on how this goes.
So like a density.
It's a density, exactly. The density is Zaremba.
So this is like yeah, okay, so that's what you mean by 100%.
That's right.
Like in the limit, you're sort of,
In the limit.
you're covering everything.
That's right. But that's very far from actually covering everything.
Right.
Right. If we unwind this, this is saying that well, this is equivalent to saying that the number
Maybe
of
like some huge error term or like
yeah, the error term. So this is equal to n plus little o of n. And we give an error rate. People now can do a power savings. But the conjecture, the full conjecture is that the number of things up to n is n plus a finite number of exceptions.
right, yeah. But
Okay,
there's like a
so
huge gap.
There's a huge gap between this and this. Okay, so we're very far from solving it, but I want to give a couple of hints on how this goes because it'll introduce some techniques that I think are worthwhile to look at, and it'll allow us to then cycle back to eventually finish Dirichlet's theorem